Well, I think that we can slowly begin this class, because yeah, we'll chat a little bit before going to the physics of this. And yeah, the first thing I would let you know is that I'm really happy some of you can put their camera on, like François, Rachel, Gosset, or Lila are doing, just because I mean it's and Ludovic right now, even though he told me that he will turn his camera off. I mean, you are not, of course, you are not forced to do that, but it's just because I really feel alone when I teach in front of my tablet, and if I see some faces, I feel a little bit better. So I'm really happy to be here today. I would love to be in front of you and not online, because I think that online teaching is just a nasty way of teaching. More particularly for the first year, I'm giving a lecture on M1 at ENS, but nevertheless we'll have to do things like that. And so I will present myself. Okay, I am Frédéric Restagno. I'm working in Orsay at the Laboratoire de Physique des Solides. So it's for those of you who are not from Paris, it is more or less 25 kilometers in the south of Paris. And I'm studying soft matter since almost 25 years. And I must say that I make this introduction about the LPS just because it is mainly a lab which was devoted originally to hard matter, to hard condensed matter, so supraconductivity and so on. And at the construction of the lab, someone was hired in this lab, and it was someone called Pierre-Gilles de Gennes. So I write his name, probably David Quéré already wrote his name several times. And at this time, Pierre-Gilles de Gennes was at the LPS to work on supraconductivity. He was supposed to, I mean, he was a young professor, and he was supposed to create a small group on theory of supraconductivity. And after a couple of years working of supraconductivity, someone arrived and was studying in the LPS. He was studying experimentally. He was studying liquid crystals, and why? Is this funny or not funny? Will that stay like that? Yeah. He was studying liquid crystals, and at this time, so experimentally, and at this time, de Gennes thought that there were some very, very strong analogies between the equations of supraconductivity and liquid crystals. So, and I think that that's something really important to have in mind, is that, well, there are some strong links between classical condensed matter classes and soft matter classes. And well, after a couple of years, de Gennes moved to Collège de France, and there is still some soft matter in Orsay. Well, at this time, soft matter didn't exist. So there were some polymer physics, some liquid crystal physics, and so on, some statistical physics, some fluid mechanics, and soft matter. The word soft matter was invented a couple of years after that. The word soft matter is often attributed by to de Gennes, but I must say that the word has been invented by a professor, which is Madeleine Vessier. I think that writing his name is important. So she was a French experimentalist working with de Gennes, and well, at the beginning of soft matter, it was more a joke. But the idea is, well, there is something in common that we can call soft matter, and that is interesting to study. And basically, it's what I want to do in this series of lectures. So if I try to define a little bit more what is soft matter for me, well, I would say that soft matter is at the frontier of several more classical science, which are fluid mechanics to some part. And these you have studied quite extensively with David Kere, at least for the fluid mechanics at interfaces. So it is also at the interfaces of chemistry, because, well, a lot of the systems that are used in soft matter, they need to be synthesized, or they come from nature, and the link between physics and chemistry is really important. Of course, there is a very strong sorry for that. Statistical physics, and I must say that the main part of my lectures will be devoted to stat phys and fluid mechanics, and of course not that much of chemistry. And, well, it is also at the corner of material science, well, probably due to these links between chemistry and material science. And, well, the last important field that I won't develop at all is the link between soft matter and biophysics. And all this can be more or less considered as soft matter. So, well, when I try to say, well, soft matter is all of these, it's not that easy to see what is in common. And there is probably some of you know Alexandra Valsac, who's studying stat phys at École Normale, and I remember we were at a conference, and we were trying to define together what is soft matter. And at the end, she said, "Well, you know, soft matter, that's like porn. When it's hard to define, but when you see some, you know that it's soft matter." So I mean, so soft matter is still something hard to define, even though there are some very strong common field regarding to what it is. But nevertheless, if I want to study what is soft matter, I would say that it is something where the energies are of the order of the thermal energies. So that's something really important in soft matter. The fact that the energy scale scales like a T. So it's really different from quantum physics, where usually, I mean, we can neglect a lot of thermal fluctuation. In soft matter, the scale of energy will be quite extensively of the order of kT, which is something like 4 × 10⁻21 joule, or 0.025 electron volt. So this has very strong consequences of what we will study. So the consequences of what we will study are mainly that, well, noise will be important. Thermal fluctuation will be important. And well, we'll have to take that all into account in order to understand the specific properties of soft matter. So we have this scale of energy. So we have also, what is also important is that we have a lot of particles. And we are dealing with dense system. So this also explains why we are really dealing with soft matter. So, and with stat phys. So really, what we are doing here in this lecture is to study a very specific part of condensed matter, but it's really condensed matter. And in this system, well, since we have a lot of particles, what we want to study is collective behavior. Well, based on that, I will give something like 7 to 8 lectures, and sorry. Okay, and well, based on that, I will give something like 8 lectures. Well, if I would be a very nice teacher, I will say that all the lecture will be 2 hours long, but I'm not this kind of guys. I mean, I will try to do that, but sometimes it will be more than 2 hours, sometimes it will be shorter than that. And what I wanted to do is to give you this kind of overview of what we will do during this lecture. So there will be one lecture on the fluctuation of molecule. So that's the lecture of today mainly. So we will mainly discuss about dipolar interaction and also polymer physics. There will be one lecture on the fluctuating charges, where we will mainly speak about the Poisson-Boltzmann equation. There will be one lecture about the fluctuation of interfaces. Where we'll speak about the fact that, well, due to this thermal agitation that we introduced before, there will be at the surface of any liquid some thermal fluctuations that will give rise to a finite thickness of the interfaces. And we will also discuss the Elfrich interaction, which is the fact that if we take a membrane, like a biophysical membrane, there are also some thermal fluctuations, and we'll see what is the spectrum of this fluctuation and how they behave, and what is the amplitude of this fluctuation. Well, since we have on all the system, we have some KT system. We will also say that, well, there are some entropic forces in all the system, and we probably will discuss these entropic forces, such as the fact that, well, there is some rubber elasticity. So if we take a polymer chain, it has an elasticity which is due to the entropy. We will discuss some depletion and interactions, which is the fact that there could be some attraction between systems due to entropic forces. And we will speak about osmosis, which is also an important phenomenon. Well, the lecture number 5, sorry, I'm always putting on this button, so I should avoid to do that. The 5th lecture will be a continuous description of the interfaces, which will be kind of an introduction to density functional theory. And then we will have a lecture about the noise and the Brownian motion. And finally, I would like to discuss about nucleation theory and barrier crossing in order to understand all this nucleation theory. So it makes eight lectures. So we have we are supposedly 8 sessions together, so I hope it will enter in these 8 lectures. Yeah, so before, so let's call that the menu. Before entering in the first lecture, I would like to know if some of you had already lectures on these things. If you think that it's completely known for you, do not hesitate to tell me. Are there some stuff that you have seen several times and you don't want to see anymore? You can tell it. I can change. No one is complaining. So Basil just left. Okay, so it seems that it's okay. I mean, really, I mean, as I told in the introduction, I mean, this for me, it's the first time I give this lecture, so I can, I mean, it's what I plan to do, but I can change to something different if you think that it's more interesting. Well, let's begin slowly now. So the first. So let's say chapter 1 or lecture 1. So we will discuss about mainly the fluctuation of molecules. So we will deal today with 2 kinds of molecules. I mean, maybe not today because we already spent some time on the introduction, but we'll speak about dipolar interactions. Yes, for the references, Anna, I think I will send you an email because I mean just writing here, I mean, or not writing. No, sorry. What I will do which is better is that I will put on the PDF of the lecture. I mean, I will give you all my notes at the end, and I will add at the end the references of the lecture. Okay. So today we will mainly speak about dipolar interactions and the fact that well, which leads to what is called the van der Waals forces. And we will also speak about the chain conformation of a polymer. Because in all this system, what is important is that thermal fluctuation are of really important to understand both the dynamics and the conformation of the systems and the forces. Well, since I'm to be completely honest, since I'm really dealing daily more with mechanics than stat phys, even though I'm using the results of stat phys, what I'm really interested in is how can we predict forces and in these systems, even though today we won't work that much on forces. So let's begin with the first part. So the first part is dipolar interactions. And I try to structure my lecture a little bit. So, well, I first go to 1.1, which is a quick reminder on dipoles. Well, the point is that, well, you all know that there are two ways of introducing the dipoles. Let's say if I introduce the dipoles from a physical point of view, I will say, well, if I have a distribution of charge Q1, Q2, Q3, oops, and in average Qy? Well, the idea is that it's possible to calculate in any points the field E. And usually, in order to calculate the field at a distance or of the center of mass of this system of charge, what we will deal is that we will study the different cases where, well, mainly if the sum of charge is different from zero, seen from a large distance, we'll say that this distribution of charge acts as a monopole, which means that, well, basically we will put all the charges at the center at the barycenter of the charge, and more or less the field will be of the form 1/4 pi epsilon dot r square u r, and oops, and here we will put the total charge of the system. Well, of course, there is an interesting case where the sum of charge is equal to 0. And why is this system interesting? It's interesting because usually the condensed matter is uncharged, so which means that in average there is no charge. Or if we speak about molecules, if they are not in the ionized states, we can describe the system by a dipole. And that's the important point. And well, the dipolar characteristics of this distribution of charge will be simply the sum of Qi Ry, where, well, Qi is the charge and Ry is the position of each charge here. And well, from that we can calculate the field, and you know how to calculate the potential and the field of this kind of distribution, and we will come back on that a little bit later. Well, so that's kind of the physical way of introducing the dipoles. And of course, if P is equal to 0, then we can go to quadrupolar interactions. But for what I want to discuss today, it's something that I will completely neglect. So, well, since matter is mainly uncharged, in a lot of situations we will be able to calculate the dipolar representation of a molecule. And if we put dipoles in an electric field, the potential energy of this dipole will be simply the value of the dipole scalar the electric field at the position of the dipoles. Well, to be completely honest, another way of introducing dipoles in a kind of soft matter courses will be not this general description. It will be more or less to say, well, in some molecule like I don't know, HCl, well, there are some inductive attraction here, since chlorine is more electronegative than hydrogen. So there will be a negatively charged here. Here that will be a positive charge. So, and in average, there will be a dipole, and let's put the physics convention from the minus to the plus, and some molecule will present a permanent dipole. Well, of course, I mean, the dipole can be permanent or can be also induced. And there's also some situation where there are some induced dipoles. And it's important to introduce the polarizability. And the polarizability can be defined as the by the relation between the dipole of a molecule and the electric field at the position of this molecule, and alpha is called the polarizability. And I know that you know a lot of things about polarizability. You have seen that in your chemistry class when you were young. And I think that a lot of molecules, they have either a permanent dipole or a polarizability, or they can also be what is somehow important. They can also present an instantaneous polarizability. And then all these dipoles, they can interact among each other and give rise to forces. So all these dipoles interactions, they have been studied quite extensively, and they have different names. So and that can be separated. So if we try to remind you the names of the dipoles interaction, if we have a permanent permanent dipole interaction, it's called the chiasm interaction. If we have an interaction between a permanent dipole and an induced dipole, it's called the Debye interaction. And if we have an instantaneous induced dipole interaction, it's called the London interaction. And well, all these interactions are really important in soft matter, and they give rise to the so-called van der Waals forces. So based on that, we can, well, as soon as we have introduced dipoles, we can calculate a little bit more than that. And we can calculate as an example, sorry, we can calculate like 1/2 the average, the electric susceptibility of a fluctuating dipole. So it's the first time where we'll try to see what is the effect of KT over a molecule. So we will study here the effect of KT on the dipole. So basically, what we want to do is, well, let's assume that we have an electric field here in the Z direction. Oops. And what we want to know is, well, we want to characterize what will be the average value of the dipole in the Z direction. So we want to calculate the average value of PZ, which is the projection of the dipole in the direction of the electric field due to the thermal fluctuation. So it's what we want to calculate. So if we want to calculate that, well, if we assume that we are mainly dealing with thermal interaction, so what we will be able to say is that, well, let's say I try to organize my whiteboard a little bit. So if it's thermal, so what we will have is that simply we'll have to average among all the configurations. So we'll say that the average projection is the value of the projection times the Boltzmann factor, and the Boltzmann factor is P E cosine of theta divided by KT times an average angle where d omega is simply the solid angle sinus theta d theta over d theta. So we have to average that. So, and if we want to normalize that, we have to put below the normalization factor, which is simply the exponential of P E cosine of theta divided by KT times d omega. Well, I think that probably some of you have already calculated that in their life. Well, if we try to go in the details of the calculation, we'll see that we can write two things. So first of all, we can write, so we can change the variables, of course. So we can say that a natural variable for this calculation is to write u as a cosine of theta. And we can also define x as to keep the same notation, P E divided by KT, and let's put a factor of minus. Did I put a factor of minus? Yes. So if we make this change of variables, then the average value of PZ is now simply the sum between -1 to +1 of Pu exponential of minus xu vu divided by exponential of minus xu du. Am I right? It seems to be okay. Well, if we write things like that, we can put that outside of the integral. I try to go slowly, and then we'll see that, well, this is minus p, and here you see that we have the derivative regarding to x of an integral. So it is p times minus d over dx of the logarithm of -1 to +1 of exponential of minus xu, sorry, du. So there was a question about, Oh yes, sorry. What is the meaning of the bracket? It means an average over time or space. I mean, here it will be equivalent. Let's say it will be an average over. I mean, it will be an average over all the configuration, the possible configuration of the molecule. Thanks, Anna, for. But so it's more or less spatial or a spatial or a time average, but so I write it. Okay, so we calculate all. For those of you who are not expert in stat phys, what we do is, well, we calculate all the configuration of the molecules. To this configuration, we attribute an energy, and we attribute the Boltzmann factor tells us the probability of having this energy. So here, you recognize the Boltzmann factor. Is that better? And do not hesitate to use the chat in order to interrupt me. So now these we can simply integrate. So the average value of PZ is now P times let's say minus P times the derivative over dx of the logarithm of this that we can integrate, and this is simply 2 times the hyperbolic sine of x divided by x. So well, this is kind of an exact value. Well, what we will deal is system where x is much smaller than 1, which tells us that we can use an approximation for the hyperbolic sinus, which is the hyperbolic sinus is close to x plus x3 over 6. Okay, so then the average value of Pz is minus P times d over dx of, I write directly the result, 1 plus x2 over 6, which is more or less minus px over 3. Okay, so which is p square e over kt, and I should write larger. So here you see something which was clear since the beginning. Well, if kt increases, if kt tends to infinity, the average value of pz tends to 0, which is clear because then it means that in average we do not feel anymore the effect of the electric field. And well, we cannot take t which tends to 0 just because we approximate the fact that x was smaller than 1. So here it allows us to see that, well, the polarizability. So here we we calculate that the polarizability due to permanent fluctuation of a molecule is of the order p squared over kT, and this is valid for permanent dipoles. Okay with this calculation? Well, the point is that there is not always a permanent dipole. So in some case, as we discussed before, we had to take into account the intrinsic polarizability of an atom, and then the intrinsic polarizability is something which is more or less that you know. Do you know what is what does the polarizability of an atom looks like? Do you remember? No, nothing in the chat. Well, what is important is that the polarizability of an atom will be proportional to its volume. That you know. You remember, at least from chemistry. No? And there is a prefactor to be homogeneous, which is the dielectric permittivity of the medium. What is clear here is, since here you see the size of the atom, you see that when we are not dealing with this kind of permanent dielectric dipoles, and we want to calculate the permittivity of the polarizability, sorry, of the atom, what we will have to deal is that we'll have to deal with quantum mechanics. Well, the size of an atom is something which is a quantum effect. So this is, here we have some hidden quantum mechanics, and that's something I don't want to study that much in this lecture. So, well, of course, since we are dealing with condensed matter, there should be some quantified effect below. Well, right now we have calculated the polarizability, and now what I want to calculate is, well, probably you have already heard that there are some important features of the electric interaction, is that the van der Waals interaction decreases like 1/R6. So let's go like that. And sorry. Well, I want to be fast on that. So if before I try to make a nice calculation here, I will make a more nasty one. So the basic idea is that if I take if I have a dipole here, P1, the electric field that is created by this dipole will be of the order P1. I mean, let's avoid the arrows. I just want to discuss order of magnitude. So the electric field P1 will be of the order of P 1 divided by R3, which is the feature of this electric field. So here, if I have if I am at a distance R, it is the electric field that I will feel. So then, if I have something like that, a molecule which is here, it will acquire a dipolar momentum, which will be the polarizability of this molecule times the field E1, so which will be alpha 2 P1 divided by R3. In return, this will create an electric field E2 at the position of the first atom, and this electric field will be of the order of alpha 2. It will be P2 divided by R3, which makes that we will have something like alpha 2 P1 over R6, and the energy acquired by the dipole, dipole 1 will be of the order of minus P1 times E2. So it will be of the order of something which will be alpha 2 P1 divided by R6, P1 squared. Well, and if we try to write it a little bit differently, we'll see that, well, P1 should be proportional to the polarizability of the molecule of the species 1. So at the end, the potential energy should be proportional to the product of the polarizability alpha 1, alpha 2 divided by R6. So this is a very crude calculation, but it's completely true. So what we observe experimentally is that the van der Waals forces decrease like that, independently of the chemistry and independently of the physical origin of this dipole. So that's something that is important. So to this point, I should make a remark. And the remark is that basically what we have said here with this picture of we have one molecule which interact with another one, and in return the other molecule interact with the first one. We have said that all these electrostatic interactions are instantaneous. So here we assume an instantaneous of the electric fields. So what is particular to this 1 over R6 is that it is what is called the non-retarded van der Waals forces. Indeed, if we take into account the delay due to the propagation of the electric field from one molecule to the other one, we'll have to deal with the fact that, well, the potential energy between two molecules will vary a little bit, and what we'll have is still an attractive interactions between two molecules, but it will vary like 1 divided by R to the power 7. And this is the characteristic of the retarded van der Waals forces. So now an interesting feature of, well, how can we know if we have to take into account this delay or not? So do you have a clue of that? And then I feel alone. No. Yeah, I mean, could think about a time scale, but it's more a question of distance, which is related due to the speed of light. But yeah, not the speed of the atoms. I think that the idea of the time scale is more appropriate. What I would say is that the question is to compare the time of light to the frequency of the oscillation of the atom. I mean, it's not homogeneous, but I think it seems fair. I mean, what we need is that when the light, I mean, when the electric field goes from one molecule to the other one and comes back, we want that the electronic configuration, the average position of the electron in the atom has not changed during that time. So it is what we want to compare. So if we say that, and if we say that, well, atoms usually adsorbed in the visible light, a way of saying that will be to say that we'll be in the range of the retarded van der Waals forces when the distance becomes larger than the wavelength of the light in the visible range. And in this regime, we'll have to go to these retarded van der Waals forces, which is okay. I mean, that's really large distances. If we deal with interactions in a lot of situations, we will be in the situation which is here. So mainly we will be in this situation in all the practical. So I read that in red. Okay, so I will always neglect these retarded van der Waals forces, even though they do exist and they should be taken into account in some cases. As an example, there has been some very nice experiments done in the past where people have measured the force between two surfaces in the vacuum or in air, and they studied the force with respect to the distance between the surface. Well, when the surfaces are close enough, we will have a signature of the classical van der Waals forces. But when we deal with large distances, so more than 500 nanometers, so then we are speaking with really low forces. Then we will have to take into account this 1 divided by r to the power 7 force. So, well, usually what we deal with are not the force between two atoms, but it's the force between surfaces. And what I want to study in this lecture is more this kind of forces. So what I want to do now. Ça marche. yes, is to calculate, well, the van der Waals interaction between two So, well, what we will make a strong hypothesis. So I let it in red. We'll make a strong hypothesis that van der Waals forces are pairwise additive. And we'll make the assumption that the van der Waals forces, well, when we have two molecules separated by a distance of r, there is a potential energy that, pairwise. So which means that we can neglect the three body interaction. So we will only consider two molecules interacting and adding the interaction. So then we will assume that the potential energy between two molecules is of the form minus C divided by R6, just as we have seen before. So if we do that, we can simply calculate the force between, let's say that we will take a small amount of matter that interacts with a half space. So here we write ρ1 the density on this side, and just for the purpose of the calculation after that, we assume that the system is not the same in the half space below. So here we note ρ2 the density. So more or less, and the polarizability here should be alpha 1, and here the polarizability should be alpha 2, which means that C should be proportional to alpha 1, alpha 2 with regard to what we have seen before. So how can we calculate the interaction of a volume d2 which is as a distance of z regarding to this half space? Well, I don't know if I want to write all the calculations, but maybe a little bit, even though I don't like that much. In the best way to calculate this interaction is probably to go in a spherical coordinate. Which says that, well, we will integrate over spherical shell here, and then we will say that the energy of interaction between this system, so this is the energy of interaction. So of course it's proportional to d2, and so it will be proportional to ρ1 d2, which is the number of particles in this square here, times rho square times, and then we integrate over the system. So it should be we integrate from z to infinity over dr. We integrate between 0 to something that I let you write here, and the force will be minus c divided by R6 times 2p r square sinus theta d theta. No, rho is rho is a number. So sorry, rho is the number of particles. Okay, well, just because. Thanks for asking. Just because but what we have said is that when we have, if I come back a little bit, what we have said is that when we have just two dipoles, they acquire a potential energy which is proportional to their polarizability divided by R6. Now, if we take an ensemble of molecules, though they are uncharged, if we take this ensemble of molecules, the total energy will be proportional to the number of molecules in the volume here, and the number of molecules in the lower volume. Does that make sense? And here you recognize the elementary volume 2 pi r square sinus theta is theta. Or I write it like that maybe. And I have already integrated over the phi direction. So here you see that if theta is this angle here, well, we cannot go from 0 to 2 pi. We have to go from 0 to the arc cosinus of z over r. Do you agree with that? You can complain. No. Do not hesitate to tell me if it's really unclear. So if I write something like that, then I will say that, well, it is minus 2 pi rho1 rho2 d2 times c, and then I integrate from z to r over dr over r square. So when I integrate the sinus, it gives me a cosine that gives me 1 minus z over r. Well, that's I can integrate properly, and I skip the calculation because I'm sure that this calculation work. Yes.
Can you explain why the limit of integration again was the arc cosine of 3 over r?
Because if I calculate here, I say, okay, I will take a sphere of radius r, which is a circle of radius r. If the value, I only take this, the theta can only varies from 0 to this limiting value. Okay, sorry, maybe I should draw a little bit differently. So here I have the limiting value of theta and all the theta values that I can use are comprised between 0 and theta and this value. And here you see by construction that this value in this triangular rectangle is arc cosine of Z over R. Is that okay now?
Yeah, thank you. Yeah, thank you.
I mean, really, I mean, I'm really appreciate. It's yes, thanks, Adrien. And if I go to these, well, I can put it minus 2 pi ρ1 over 2 d2. Let's put the calculation properly, and it's minus 1 over 3 s square plus z over 4 r4, and then I calculate between z to infinity, and then double is simply minus 2 pi c ρ1 ρ2 divided by 12. That's putain, pardon. Okay, so this gives me the interaction between the small volume dito and the half space. And what we are interested indeed is not the situation. What we are interested is more the situation where we have two half spaces separated by a distance d. So if we want to calculate that, what we want is to calculate P of d, the total energy due to van der Waals forces between these two half spaces. Per surface area. So if we want to do that, we will say that simply that P of d is the integral of these. So it minus 2 pi c ρ1 ρ2 divided by 12. Sum from d to infinity. Do you agree with that? And then we can calculate these, and I give you the result. It is minus P C ρ1 ρ2 divided by 12 B square. And this, sorry for that, people are used to write it in the following form: minus A over 12 pi D square. So where they have written that A is simply P square ρ1 ρ2 C, which is P square, which is proportional to, sorry, ρ1 alpha 1 ρ2 alpha 2. And this value of A, it is called the Hamaker constant. Well, this tells us something interesting, is that when we have two molecules, they interact like 1 divided by r to the power 6. But if we take an ensemble of molecules, if we have two half space, so this, and what is important is this is a strong decrease related to the distance. But if we have two half space, then now we have P over D, which is of the form minus A divided by 12 pi D square. And this is a slow and this explains why between two half spaces, van der Waals forces can be important. Okay, so now so here what we have done is calculating the interaction between two half space, and from that we can discuss a little bit the order of magnitude. Since I am an experimentalist, I like, can I switch to the next one? Tell me if it's, well, what is important now is to deal with the order of magnitude. So, well, the first thing is we always observe that if we try to measure to measure A, it's in the range 10 to the minus 20 to 10 to the minus 21 joule. It's homogeneous to an energy, and it's not that much dependent of the kind of molecule. I mean, of course it depends, but the range of Hamaker, I mean, it's only a factor of 10, so not that much different, not that much dependent of the chemistry. Then we can also try to think a little bit about, well, what we have seen is that A usually is positive for as an example, if I take 1 and 2 and vacuum, like we have done, which means that between two condensed phases, the van der Waals forces are always attractive. But there are also some empirical rules that are useful for experimentalists, not that much for theory, or, well, depends, which allows us to give kind of orders of magnitude for the Hamaker constant. Well, the first one is that if I say that I have a system with, let's say, if I have a system where I have 1 and 1 interacting among vacuum, I will define what I will call the A11 Hamaker constant. So it's a Hamaker constant for a symmetric system. If I take a 1-2 system with vacuum, well, I will define A12 Hamaker constant. And it's kind of easy to convince yourself, I think, that A12 will be of the order of magnitude of A11, the square root of A11 times the square root of A22. It is just due to the fact that this should be proportional to the density in times the polarizability. This should be proportional to the density to the polarizability, and this should be proportional to ρ1, ρ2, alpha1, alpha2. So I think that it will be easy to convince yourself that there is kind of a relationship between that. But more interestingly is what happens if I try to study a more complex system where I have a system 1, a system 2, and instead of putting some vacuum inside, I put a system 3 in between. If I do that, well, what I would have to do is calculate the interaction of 1 over 2, 3 vacuum, plus add the interaction of 1 over 3, plus the interaction of 2 over 3, and so on, and add all the calculation. And if I assume that the expression of the Hamaker constant are of the same order of magnitude, what I can show, and I won't do today, is that the Hamaker constant for this system, so what I will write 1, 3, 2 to say that 3 is in between 1 and 2, is approximatively the square root of A11 times the square root of A33 times the square root of A22. It should be symmetrical. Times the square root of A33. And this becomes interesting because this was, of course, always positive, which means that 1 loves 1. This is always positive. This means that 1 loves 2 if there is in between some vacuum. But this can be positive or negative depending on the value. And this is really interesting. So we can give some examples. A very common example is a situation where two is a solid. Oops. Three is a liquid. And here we have a gas. I mean, that's a situation very close to the situation that you have studied with David Quéré, where you put a liquid on a solid, okay? And if you have this situation, so what you will have is that the Hamaker constant, which tells us what is the global average force between the surface, will be, well, in this situation, the Hamaker constant of A11 will be close to 0, just due to the fact that the density here is small compared, the density in the gas is small compared to the density both in the liquid phase and in the solid phase. So if we have that, so A1 through 3 will be minus A33 times the square root of A22 . So now we see that what we have to compare in order to know if the van der Waals leads to attraction between the surface or repulsion between the surface, we have to compare these two values. So, well, since 2 is a solid, can you imagine a situation where A22 is larger than when 833? How would you do that? Any idea? Any guess?
But maybe by taking a material which has a very low polarizability.
So yes, so here exactly. So what you want is to say is here you want something, a liquid with a low polarizability. And here a solid with a large polarizability. So how can you do that? What, I mean, make a guess. No guess? Well, would you agree that a metal is something which is hugely polarizable? I mean, you apply an electric field and the electrons will move. That's the worst case we can imagine. So if we take a metal here, and here if we take like something like, so Amélie says oil on the magnets. Well, it's it's for the liquid, I'll agree that we need oil. For the solid, I would say a metal, because here we are dealing with electric susceptibility, not magnetic susceptibility. Do you agree with that? So if we do that, what we with this kind of system, we will end up with an Hamaker constant which is negative, which means that when we put the oil here on the solid, there is, in average, a resulting force between the two spaces that tends to thicken the liquid layer. Well, then if we go to the contrary, if we try to imagine a situation where we have an Hamaker constant A22 which is smaller than A33. So what can we have as no, we want this one to be like a plastic. Okay, and this one, like, let's take a metal again, or water, which is something with kind of large dipolar momentum. Then with this situation, we will get to the more classical situation where the Hamaker constant will be positive. And then is in this situation, the van der Waals forces, they tend to make the two surfaces close to each other. So this so this is really interesting, because depending on the kind of system, we'll have something which is different. If I tend to make the link between this lecture and the lecture by David Quéré, what will be in terms of wetting, what will be the situation where you have oil on the metal? Will that wet or not? Do you know that? Or at least experimentally? Oil on metal, you know the result. More than water on plastic. Good point. Well, you can do the experiment in this situation. What you will see usually is that you will be in a situation of total wetting. And here the situation where we have water on plastic or metal on plastic, but liquid metal, so which makes mercury on plastic. And here we are in a situation of partial wetting. So which means that at the end, so I kind of insist on that because I think it's a little bit counterintuitive. Here what you have is that in this situation, usually when you make a drop of liquid, you will be in this situation. Whereas in this situation where, in terms of wetting, you put the liquid, you will be in this situation. So you see that if we think the problem in these terms, it seems that here we have said that the van der Waals forces they tend to thicken the system in a situation where we are in a total wetting, and here we say that the van der Waals forces they more or less tend to make the system thinner when in a situation where we are in partial wetting. But this is due to the fact that we are dealing with scales which are not exactly the same. And here we are mainly dealing with situation where we are looking at large scale. And if we see it in terms of what happens here, the van der Waals forces as tend to make the system thin here at the border. And here what happened is that in average the system has flattened due to the wetting, and at the end the van der Waals forces they will tend to stabilize this liquid layer. So it's okay. So I mean, to conclude on this side, what we have seen here is that we can find some kind of empirical rules to predict the sign of the Hamaker constant. The Hamaker constant, which is the amplitude of the interaction between two surfaces, can be either positive or negative, and the sign of this Hamaker constant will depend on the polarizability of the molecule. And the link between, the sign of the Hamaker constant and the wettability is not that a very trivial point to have in mind. So I would like to say something a little bit about this, the validity of the calculation we have done. Well, I just want to come back to the fact that what we have said before is that I come back to that. We have used the pairwise additivity a lot, because when we have calculated the overall interactions between these two spaces, we have said, well, we have a dipole 1, it interacts with a dipole 2, and we have completely neglect the fact that dipole 2 interact with a dipole 3 and the way all these kinds interact. So, well, and this is largely false. I mean, at least for the it should be true for the Chisholm interaction, but it's probably completely false for the London interaction. And well, so at this point we should say, okay, why have we done all this calculation if it's false? Just because in the 50s, a group of theoreticists in Russia, led by Eugene Lifshitz, the one from the Landau Lifshitz book, they said, well, we can calculate the force between systems, but using a completely different way of calculation. They used a continuum electrodynamic point of view. So this is completely out of the scope of this lecture, but the way they are calculating that is that, well, they say simply that, well, not simply, that's awful calculation, or at least for me. What they have calculated is they said, well, we can calculate as an example what will be the energy of an electric field if we put again vacuum. And if we take a half space of permittivity epsilon1 of omega, and here 0 and epsilon1 the omega. So what they have done is that they calculate the electric field, the magnetic field, and the energy of that. And if you do that, you can show that what we have seen just before about the shape of the energy per unit area is still valid. So you will still be able to say that the energy per surface area between two half space is of the follows the expression minus a times 12 by d squared. And now they calculate A with this kind of approximation. And I just give you to see what are the ingredients in the results of their calculations, how this equation looks like. And as an example, they say that the energy, the Hamaker constant here for two half space of the same nature is of the form 3/4 of kT, and then you have the value. Oh no, here it's 2. Sorry, it's not a. Sorry, I'm wrong here. It was not I mean, the calculation I've done here is I've not done. Sorry, it's 2, and the Hamaker constant here is that I've taken in the books is A1, 2, 1. So for the sandwich of 1 to 1, and it is epsilon1 of 0, epsilon2 of 0 divided by epsilon1 of 0 plus epsilon2 of 0 to the square plus 3 h bar over 4 pi sum from kT over h bar from infinity So here, epsilon1 over 0 of omega is the complex permittivity. Of the material. So what you see here is that, well, here, since you have something which is proportional to KT, you see that the first part in the Hamaker constants is largely entropic. And since it uses zero frequency permittivity, the first term here is more or less allowed us to characterize both the dipole-dipole or the dipole-induced dipole interaction. Whereas this term, which take into account all the high frequency term in the permittivity, they are more likely to represent the dispersion interaction. So to be clear, I mean, I will never ask you anything about that. The only thing I want you to keep in mind is that what we have here is we see that we have both something which is more or less of a kind of classical nature, and here we are more or less something which is more of a quantum nature. As you can see by the fact that there is here this Planck constant here. But nevertheless, what is important is that in all cases, we will be able to say that the interaction between two surfaces follow more or less what is predicted by our simple calculation. So what we will use in the future is the shape of this Hamaker force constant. And these you have a little bit discussed that before. Sorry, what do I mean by dispersion interaction? It's a London interaction. Thanks. What did I want? Yeah, you had already discussed a little bit this kind of interaction between flat surface with David Quéré. Do you remember when? We will use that in next lecture, because I need another part in the calculation that we will do next time. But you discuss the fact that there are attractive van der Waals forces between surfaces that can be sometimes, yeah, you discussed that before. No? No one make a try? So this is 1/2 of the calculations that we will need for the DLVO force. And go say you're right, in wetting phenomena. And the DLVO force, you used it in what part of the course? Do you remember? Well, at least for the stability of foam films. And in particular, you discuss with David the Newton black film. No Cassie. In Cassie-Wenzel, there are no. I mean, Cassie-Wenzel theory is a more likely Cassie is a more macroscopic term. Yes, Julien, you're right. It explains Bebel stability. I mean, so again, to come back on that, here in the liquid film, what we will have, but we'll see that next time. But in the liquid film, we have air, liquid, air. So we are in a symmetric case. In a symmetric case, the van der Waals there is always a van der Waals attraction. So the van der Waals force is not the cause of the stabilization. So the van der Waals force is more or less a cause of destabilization of liquid film in or bubble films. So the origin, the important terms for the stability is more the electrostatic term. So I want now for the last 10 minutes. Sorry for that. Discuss now another kind of interaction where we have also where we have strong fluctuation terms and strong entropic term. And the second part of this lecture, so we will, as I said, it was supposed to be one lecture, but it won't. I mean, the second part of the lecture will be devoted to the polymer conformation, and I will today only make the introduction on polymers. And you will see already some polymers during the tutorial after that with Alessandro Siria, and we'll come back on more easy way, I think, next week. And well, the only thing I want to do today is to come back to the elementary polymer chemistry. Well, just because it's a very an important part of soft matter. So what is really interesting in polymer is that they have a very common properties, despite the fact that they can have a very different chemistries. And these properties, as an example, they can be, well, the common properties of polymer is that they have highly elastic. In comparison to metals, as an example, they present viscoelasticity which makes them both elastic and fluid. When they are charged, they can absorb a lot of water. So charged polymers are called polyelectrolytes. And well, I think that for a physicist, it's really important to understand what is what kind of physics we need in order to understand what is common in all this polymer. So a polymer is an ensemble of monomers which are connected and which are called monomers. And usually there is a large number of monomers. So the number of monomers in the polymer chains for people using chemistry, it is called the degree of polymerization. And usually they note it. UPAC proposed to note it with a very strange sign, which looks like that you don't have to recover except if you want to do something. And well, when I say that it's a large number of monomers, it's the number of monomers in a chain is usually comprised between, let's say, 10 to the power 2 to 10 to the power 5, which is kind of a lot. And the most common polymers that we have is that like the polyethylene. So the polyethylene is the chemistry is this one. So you see that it is we could say that this is a monomer, but because you have that a lot of times, but due to the way of synthesis of the polyethylene, we rather say that this is a monomer. Another very common class of plastic or polymer are the let's say, well, let's talk about this one. Polystyrene. So this is CH2CH, and then we have a benzyl ring. What kind of polymer do we have commonly in our daily life? We have the polyvinyl chloride. And maybe, I mean, and if we stay with the classical polymers for physicists, I think that David Quéré told you about a lot of experiments which were done with PDMS that probably people also call silicone oil. So these polymers have a chemistry which is this one. So it is now the backbone is a silicon oxide silicon chemical bound. And they look like that. So a lot of experiments done with wet for the physics of wetting are done with PDMS. Due to the fact that it allows to change the viscosity like the one, I mean, if you want to test all the scaling laws that you have seen with David, where you change the capillary number, which means that you change the viscosity and so on, without changing the chemistry, PDMS are a very good candidate because you can have a large range of viscosity, and we will discuss a little bit why it's easy to change the viscosity with PDMS without changing anything that and without changing the surface tension. I mean, all these one here, polyethylene, polystyrene, and PVC, they are solid at room temperature. And this one is liquid at room temperature. And of course, I mean, among all the polymers that you have to deal with in daily life, you have DNA, which is a very complex one, which is a charged one, and that I won't study at all during the couple of lectures where I will speak about polymers. So the idea is with polymers that we will deal with is that there is a large number of polymers, and the fact that a last thing that is really important is that in the molten state, let's say the liquid state, but usually for polymer physics we prefer to say molten states. The chains more or less look like that. So they look like they are coils, and they are really different from rods. And the fact that they adopt a coils conformation gives them these unique properties of polymer physics. Okay with that? So well, here today I just simply written the basic of the elementary chemistry of polymers. What you will do with Alessandro, you will write some kind of statistical physics of polymers in order to understand what is the probability of having a certain conformation of the polymer chains. And what we will do in the next lecture is more or less, well, come back to this to what you will discuss with Alessandro today, and probably also we'll discuss about the way experimentally, because it doesn't look like that, or maybe, well, I don't know. I will discuss you about what is the technique that we can use in order to find the conformation of these polymer chains, and we will come back to the second lecture. We will be the systems where we have charge, because up to now I mean, the only way we have discussed charge is when they are positive plus negative in the dipole, and we will discuss more electrostatic interaction. So I think I have to stop here because I want you to have a break between the lecture and the tutorial, but I'm open to questions.